in search of soil.
Knowing what you know, what are some of the misconceptions from an agricultural producer standpoint around clay?
First of all, clay has several meanings. It's defined sometimes as a particle size, just any particles that are less than what we call 2 microns, which is a little almost too small to see. Okay, but it also has a meaning in terms of mineralogy, the chemistry and the structure of the atoms that make up that clay particle. And there is a whole large family of different types of clay minerals, and they have different properties, and depending on the amount of clay and the type of clay that you have, can have a big influence on soil properties. So I think recognizing that clays are actually minerals, that means they have a 3-dimensional structure. The atoms are not just randomly scattered around, they are in very specific structure, and that impacts the properties of the clay. And another area where people probably don't have fully appreciate or often appreciate is that clays evolve with time on a grand scale, and they are hugely influenced by climate. So if you go down into the tropics, you'll find very different types of clays in the soil down there than you will up in more temperate regions. Here in the Midwestern part of the US, you find what we call smectites, 2-to-1 phyllosilicates. These are sort of like, they have this kind of the structure of mica, flat, and they're made of silicon, aluminum, magnesium. But you go down into the tropics and you find a whole different group of clays that are dominated by iron and aluminum oxides. And they have evolved as the soil weathers through the influence of climate. Certain cations are leached out of the clays. The clays begin to structurally reorient, and you end up moving towards these oxides. And there is a systematic pattern or process by which this evolution or weathering of clay minerals occurs.
Does that aging of clay affect agricultural productivity of soils? In other words, if you had a predominance of a certain type of clay in a soil, could you suppose that all else being equal, that soil may be more productive than a different soil, a different evolution of clay?
Clays have a big influence, but there are also other factors that influence the productivity of the soil. Clays are just one of the factors. But yes, the type of clay matters. So here again, in more temperate climates, we have, and we mentioned these smectites, this mica-like clays, and they tend to have high ability to retain cations, a term called cation exchange capacity. On the other hand, if you go down to the tropics, the oxide clays, iron, aluminum, oxyhydroxide phases have a much lower ability to retain cations. And also, they influence the pH buffering capacity, and I don't want to get too deep in the terminology here, but pH is how acid or basic the soil is. And if you add, some hydrochloric acid or more acid to the system, how rapidly that pH changes. Well, the clays that we have down in the tropics are very unbuffered. They can become very acidic very quickly, whereas the clays that we have in temperate regions resist change in pH. So a farmer adds ammonium forms of fertilizer, very critical for crop growth. Nitrogen exists in ammonium and nitrate forms. And that ammonium tends to acidify the soil as it is transformed. The soils in the temperate regions resist that acidification. They still need lime periodically, but the soils in the tropics will acidify very rapidly and often are already acidified. So yes, it makes a big difference in the ability to hold nutrients and in the influence on soil pH, soil reaction. Sometimes pH is called soil reaction. And those have a big influence on crop productivity.
Can you talk a little bit about cation exchange capacity of clays and why that's important from an agricultural perspective?
Okay, so a growing plant, we all know they need nitrogen, phosphorus, and potassium or potash. Sometimes potassium is called potash, right? Those are important macronutrients for a crop to grow in. But they also need other elements like calcium, magnesium, and metals like zinc in lesser amounts. Okay, if my hand is a clay mineral, if it's one of these smectides, they have sites of what we call isomorphic substitution. Basically, in the structure, we have an aluminum atom or we have a magnesium atom where an aluminum atom ought to be. And that creates a negative charge, which is manifested on the surface. So just think of a little minus sign right here on my hand, and that minus sign holds a cation. It attracts it. But if I'm down in the tropics and I have oxides, which don't tend to be platy, they're more globular in nature, they don't have those negative charges. They're not able to retain a cation by electrostatic attraction, which means the cation is free to leach when it rains.
From a mineral standpoint, sand versus clay.
Okay, well, sand, beach sand, is dominated by quartz, SiO2, silicon oxide. Quartz exists as roughly a not quite spherical, but about equidimensional particle. Okay, and quartz particles, those surfaces on the quartz particles, they can have a positive charge, a negative charge, or a neutral charge. They have a positive charge when they're in a very acidic environment. You put them in acid. They have a neutral, they have a basic or a negative charge when they are in a very alkaline environment. You put them in sodium hydroxide, right? But across most of the range, pH range, where crops are grown, where soils of agronomic value, those quartz particles have a neutral surface. They do not have either a positive or a negative charge. So varies as a function of pH. They have very low surface area. Even okay, so if you look at the mineralogy, it's dominantly quartz. There are other minerals in there. There are minerals called feldspars and a number of other phases, but by and large, sand is hugely dominated by quartz. Okay, clays are not quartz. They have some silicon in them, but they also have aluminum and iron and magnesium, and they have a very different morphology, and they can have enormous surface area. So if I have a 1 gram of sand, so about the tip of my thumb there of sand, that might have a surface area of, let's say, a 1/10 or even 100th of a metered square per gram. So very small. If I had 1 gram of a fully expanding smectite, a montmorillonite so smectite's kind of a family name. Montmorillonite is one of the members of that family. It can have a surface area of almost 800 meters squared per gram. So an enormous amount of surface area. And on those surfaces are those negative charges we talked about before. So your quartz particle is essentially tiny amount of surface area and neutral. Your clay particle has enormous amount of surface area and charge sites on those surfaces. Those charge sites hold not just one cation, but millions and billions of cations. And the cations and the charge sites hold water. Okay, the quartz particle, the water just runs right through it, doesn't stick. The clay particle, the water forms a nice film of water around it that encompasses those cations and those charged surfaces.
If we took a quartz particle and we round it down to make it equal size of a clay particle, so size was no different, would they both have similar surface area, or would the clay still have a lot more surface area, and if so, why?
Okay, so this really gets to a very complicated question of what is particle size. We operationally define it by a method that we use to measure particle size. We put some soil in a tube with water, and we disperse it. Till it's a nice uniform, homogeneous, and then we measure the density of it with a hydrometer. One of those things you measure the sugar content of a wine or the alcohol content of a wine. And we measure that as a function of time. And of course, the sand particles settle out first to the bottom of that tube. And then the silt particles, which are different size between sand and clay, settle out. And then clay stays in suspension for a longer period of time. And so we put a model together, a mathematical algorithm that assumes that those particles are perfect spheres with a certain density to it, and how fast would they settle. The reality is that quartz behaves about like we would expect it to in our mathematical model. By the way, that model is called Stokes' law. It defines how fast a particle of a certain size and density settles in water. But clays, because they are very thin and have very wide surfaces, they actually settle more like a parachute. Okay? They don't, you know, you drop a rock and it goes down, you drop a parachute or a leaf and it goes down very slowly. And this is because of the shape. So you say that they are less than 2 micron particle size. That's a clay, right? That's how we define it. But that means what we call equivalent spherical diameter. Okay? Reality is you can have smectites that are tens of microns across, bigger than your silt particles, but they will settle much more slowly because they behave like a parachute. So when we say particle size, it gets confusing as to what you really mean. Are you talking about equivalent spherical diameter, or are you talking about the actual physical dimension of the particle? And if you're talking about the physical dimension, are you talking about it in the XY plane or in the Z plane? Because they can be extremely thin, like a sheet of paper, literally, you know, just imagine a sheet of paper floating in there, very, very thin, but big XY direction. So to get back and try and answer your question, if we could grind a quartz particle down, and we can, it would increase the surface area, but nowhere near as much as you have with these smectites. Furthermore, what would happen is that the quartz would dissolve very quickly. If you look at the mineralogy of clays, you find quartz in the coarse clay fraction, that is in the greater than, or the size that is between 0.2 and 2 microns. You'll find quartz there, but you won't find quartz in the less than 0.2 micron fraction. Okay? However, these smectites, because they behave like a parachute, so if you use equivalent spherical diameter, they are all less than this 0.2 microns. They could be tens of microns across, but they behave like they are a parachute moving down through that water. They don't settle very fast at all. But there's a very different mineralogy down there. They do not, they are stable, whereas quartz, if it were that fine, would be unstable, would rapidly dissolve, disappear. I don't know if I fully answered your question.
You
but
did, and it's really fascinating, and I'm glad you went to that extent to answer it. So a clay particle is essentially a clay particle forever, and I know a geological time scale is a very long period of time. They evolve, but they never, and I'll say never, but I don't mean never, like it takes a very, very long time for that clay to dissolve like the quartz would dissolve relative.
It just depends on the soil environment.
Okay.
Okay, so these smectites are stable in a temperate region soil. But if I took that smectite down to Brazil and put it in a oxisol, a really old soil down in the Amazon jungle of Brazil, that smectite would decompose, degrade very rapidly. Maybe not overnight, you understand, but in a year or two, it it would disappear. But it would persist, and it might even grow in a soil here in Iowa. So the environment makes a difference. And what is the big difference? A lot of it is the pH, how acid or basic that soil is. The soils down in the Amazon tend to be quite acidic. They also are leached of what we call base cations, cations like calcium, magnesium, potassium. Those get leached out of those soils down there, whereas they are enriched in our soils in the Midwest. And the presence of those cations has an influence on the stability of the clay and how fast that clay can be decomposed or changed.
I don't know if you know this or not. I'll take a shot at this question. Is there anything related to clays that made it possible for the Great Plains to evolve to be what they were?
First of all, we also need to understand that depending on where you are in the Great Plains, there's a big difference in time. So I need to back up one step. In classic literature, there are 5 soil forming factors. The parent material, what type of rock, is one of those. The climate, is it hot and dry? Is it wet and hot? Is it cold? Has a big influence on soil formation. Biology, and by biology I mean obviously plant communities, but also the microorganisms, and you could even throw human beings into that biology piece as well. Topography is another soil forming factor. So if you are up on top of a hillside or if you're down in a valley, it makes a big difference. Material moves is eroded off the hilltop and settles out down in the valley bottom. But also water moves through the soil laterally downhill towards that valley. And it leaches nutrients, cations from up high and carries them down, salts, and so on. The 5th soil forming factor is time. Okay, so when you go into the Great Plains, and I'm located in Ames, Iowa. All right, 14,000 years ago, where I'm sitting right now, there was, I don't know, somewhere like half a mile of ice above my head. I'd be at the bottom of a massive glacier. Okay, well, when that glacier came marching down out of Canada, it was like a giant bulldozer. It ripped all the soils from the Canadians and from northern Minnesota and brought it down here and dumped it here in central Iowa. It took giant boulders and ground it up into flour. Okay. On the other hand, if I go down to, let's say, central Kansas. Okay, so sorry. So my point was that the soils here in Iowa are actually very young.
Okay.
They're babies as far as soils go. But I go down to central Kansas and they're very old. Hundreds of thousands of years, maybe, I don't know. Depends on where you are. If, sometimes you've got areas that are eroding and depositing, and those would be younger. But if you have a stable surface, That soil could have been there for a very long period of time. And we talked earlier about how clay minerals evolve with time. So imagine that after the glacier came down, right, I ground up a rock, and that rock had in it mica and feldspars and quartz and other primary minerals that got ground up into flour. Okay. And then the glacier melts away, and we're left with this pulverized rock. Well, then these soil forming factors start impacting that pulverized rock, the climate, the biology, the topography. What am I missing? Time, and I forget what, I've dropped one here. Those factors start influencing the evolution. And so you have chemistry going on, you have biology going on, you have physics going on in that soil environment. And particles of primary minerals tend to be unstable. They tend to dissolve. Okay? On the other hand, clay minerals actually start to be nucleated and start to grow right there in the soil. And some clay minerals are, like if you have a mica, a muscovite, right? You've all seen the big sheets of muscovite. Well, that's very similar to these clay minerals, but I can sort of change that a little bit. There's iron in that muscovite, not a lot, but there's a little bit. And I can oxidize that iron, turn it from a 2+ to a 3+ phase. Okay. And when I do that, it changes the amount of charge on that surfaces. Okay. The mica will start to open up. The individual layers will open up. It'll get physically broken into smaller and smaller particles. The potassium, which is sitting between each of those layers, gets leached out. Plants take it up. And so there's what's called a solid state transformation, where I can take that mica and turn it into smectites. But there's also neogenesis, which is another process in which smectites form by precipitation reactions. They start literally chemically building on top of each other and grow right there in the soil. So we have some of both of those going on in the soil environment. And so the 14,000 years that since the glaciers left right here in Iowa, in central Iowa, have been enough that we've made some smectite. Not a huge amount in many cases, but some. But if I go down to eastern, south, central Kansas now, we've had a long, long period of on a stable surface, not an eroding or depositional area, but on a stable surface. Been a long time for weather to influence and biology to influence those soils. And the smectite, the easily weathered minerals have, pretty well weathered away. You've formed lots of these smectites. Go further south, down into Georgia, and the smectites start transforming into another mineral called kaolinite. You're probably familiar with kaolinite because it's often used in making pottery. Okay? But the smectites have very unique properties. They can shrink and swell. They can imbibe water between each of the layers. The kaolinite doesn't do that. It's the transformation that occurs is the loss of silicon. So, all right, now this is going to get really deep in the weeds, but in a smectite, we have what's called a 2-to-1 layer. So you've got a silica tetrahedral layer, an aluminum octahedral layer, and another silica tetrahedral layer. 3 layers. Basically, that's 4 oxygen atoms thick. All right. What happens in a kaolinite is one of those silica tetrahedral layers disappears. And I have a silica tetrahedral layer and an aluminum octahedral layer left. So I have leached silicon out. I go further south, down into the Amazon now, and the kaolinite starts to, there's still a lot of kaolinite in the Amazon, but it starts to disappear, and I'm left with just iron and aluminum oxygen. So in other words, this time factor that influences soil formation and clay evolution involves the leaching of what we'll call base cations, so calcium, magnesium, potassium. They tend to get leached out first, and then silicon gets leached out. And finally, we're left with nothing but this iron and aluminum oxides. Minerals like goethite, lepidocrosite, gibbsite. These are the minerals that are the clay minerals that are left behind after this process of evolution.
So if I put, say, a common plant, corn in smectites, corn in goethite, is the plant going to know the difference between the two or perform differently given what's leached out of that clay when you go from smectite to the Amazonian clay?
The corn plant growing in Amazonian soils is going to be deficient in calcium, magnesium, potassium, a lot of these cations that are really important for crop growth, unless I'm putting those on. I can put lime on, and I can put potash on, and I can make those oxasols productive. Okay. I usually don't have to do that if I've got a smectite-rich soil.
Well, let me pause you there. Is that because the smectite is holding it, or are the minerals within the clay biologically available? So some microorganisms in the soil can put out acids or enzymes that dissolve that clay and break it down. Can they go do that from clay particles?
Yes, if you have a, okay, so this is complicated, but if you have a primary mineral like a feldspar, okay, this has some potassium in it, and it is slowly being dissolved away and slowly releasing potassium, and plants are taking it up. If you have a mica, a muscovite, it is slowly being weathered. The layers are opening up and releasing potassium. Once they get in the solution, plants or microbes can use that potassium. The same with calcium. Calcium isn't found inside of micas, but it certainly can be found inside of feldspars. Okay, magnesium. So you can weather those and release those base cations. And as long as there's a balance and equilibrium, as long as they're primary minerals to be weathered, you're going to have a certain population in the soil solution, which will be there for the plants. You go down to these oxasols down in the tropics, and that's gone. There's no reservoir of those cationic nutrients left. you have to throw it all on top in terms of lime and fertilizer. In fact, in the tropics, most of the nutrients are actually in the organic layer, the litter, the leaves, and the biology. And if this is kind of an interesting phenomenon. I diverge slightly, but we have these incredibly weathered soils down in the tropics, and yet they support the greatest biome on the planet, the rainforest. Sounds like a contradiction, but there's a reason for that, and that's the biology. A leaf falls to the ground in the rainforest. It hits the ground, and there's potassium and calcium, magnesium in that leaf. But as soon as it hits the surface of the soil, there are organisms, fungi, bacteria, actinomycetes that eat up that leaf and recycle those nutrients back into the rainforest. So it's a closed system. Those nutrients are continuously recycled. But if I come in and slat and burn, cut away the rainforest, then I disrupt that biological web. And what nutrients are there quickly get leached out. And then the rainforest, the tropical forest, soils cease to be productive. Whereas the soils here in Iowa are intrinsically rich in these nutrients and can produce them through the slow weathering of these primary minerals. Now, the smectites, as I said, they tend to be stable in this market. So they're maybe not going to weather as rapidly, unless I start taking them down to, like Georgia or Alabama or someplace, then they're going to start weathering and disappearing. And they will release some nutrients as they weather.
Being very simple is one of the huge benefits to an ecosystem for these smectites, these clays, is they provide a stable source of nutrients that's accessible, but it's there over a very, very long period of time.
I think the key thing about the smectites is the cation exchange capacity, those negative charges that we talked about earlier, because they will hold cations and prevent them from leaching.
But the smectites themselves, are they, they have minerals making them up.
Yeah, elements, yep.
Elements. Is the biology going in there and saying, okay, I'm going to take this smectite, and the smectite itself it's ABC components, and suddenly now they're free floating. A is by itself, B is by itself, C is by itself, because they've broken those bonds, and the smectite is no longer a molecule.
That process can happen. Again, if you start moving towards warmer, wetter environments, like down in Georgia, the smectites will slowly disintegrate. And they'll go from this 3-layer system to the 2-layer system. Okay, and during that process, there will be the release of any of the exchangeable cations, which could be calcium, magnesium, potassium, for example, that are held between the layers. That will be released to the soil solution. Plants will take it up. Eventually, if we start weathering it, they'll be leached out. Within the 2-to-1 layers, there is some magnesium, which is an important nutrient, but there isn't a lot of other nutrients. It's mostly silicon and aluminum, magnesium, and some iron are the dominant elements inside the structure. The exchangeable cations, or the interlayer cations, those are the real reservoir of nutrients for the plants. So think of I'm looking for a book here, right? A manuscript. I've got a book, right? I've got a bunch of pages in this book. And all of the letters on those pages are like those negative charge sites. And each one of those is holding a nutrient that, could be a potassium or a calcium, right? And but the pages of this book, can be separated. I could take it. Now I've got two pieces, right? All right. So the answer is yes, but it's not the minerals that are inside the 2-to-1 layers. It's the minerals that are between the 2-to-1 layers that the smectite provides.
So those cation exchange points, you have minerals held there by charge.
Mm-hmm.
There's a bond there. What in biology produces something strong enough to break that bond, to release it? The plant needs it. How does it get off that point? How do you dissolve that bond?
So if we're talking about a smectite surface where we've got a negative surface charge site on that surface, and I've got a positively charged cation, the interaction that holds that cation to the surface, the chemical bond, is primarily what we call an ionic bond. It's just a positive negative charge thing, where the negative charge attracts the positive charge. The only way you get that cation off is if another cation comes along and knocks it off, trades places with it. Okay? That other cation can be a proton, an acid, right? So a hydrogen atom, which has a +1 charge to it. So I could have a potassium cation held on this clay surface, and a proton, a hydrogen atom, hydrogen ion comes in and knocks it off and takes its place. I'm left with the hydrogen on this smectite surface. The potassium is now in solution, and the plant can take it up. Plants will release acids from their roots with the very deliberate intent of extracting the nutrient cations off the clay surfaces.
Is that hydrogen bond in the acid more attractive to that negative charge point than the cation's positive change? In other words, I guess what I'm getting at, how does it, positive charges going after one negative, how does one knock another one off? If they're both equal strength, why doesn't the cation just hang on?
Okay, so this is the heart of cation exchange. And well, actually, it gets really deep here, but first of all, there are billions and billions of cations swarming around continuously. Some of them are held very tightly to the surface, right next to the surface, directly touching the clay surface. But some of those cations, think of this eraser as a cation, are actually surrounded by water. And the water, there's a layer of water between that cation and the surface. And now I've got a proton out here, or another cation, which is also surrounded by water. And that can come in and just sort of by like bowling ball or like billiard balls, right? You shoot a pool, right? You shoot a ball across the table, it hits another one, bing, and it flies off. So just by kinetic motion, the movement, you can like a billiard ball. Hit one ball, knock the other one off. That one stays behind. And that's going on billions of times a second in a gram of soil. Okay? And it's a matter of statistics. If I start putting in acid in there, hydrogen atoms that have a positive charge, eventually I'm going to be leaching out the exchangeable base cations like potassium, calcium, and magnesium.
And the plant's able to then, is this another ratio thing where there's so many that have been knocked off that the plant can soak them up before the ones that get soaked up reattach?
Yeah, well, it's statistics,
Right.
You have to realize that plant roots, if you have and this really gets at the heart of a lot of things. If I have a prairie or a sod grass, right? I've got solid surface cover, but I've also got millions of roots that are through the soil. But not only do I have all those roots and root hairs, which are submicroscopic, but I also have a fungi, mycorrhizae, that is living symbiotically in those roots. And the fungi have what are called hyphae, little tiny threads. And literally in that sod, or in a native prairie, I have a root hair, or a fungal hyphae that is traversing every cubic millimeter of soil volume. It's everywhere, okay? And they work together to take up nutrient ions. The fungi might take it up and give the nutrient to the plant, and the plant would give some sugar, basically, some food, nutrient to the fungi, to the mycorrhizae. And that symbiosis that's going on. Now, if I go into a row crop field, okay, well, all right, now think about it for a moment. I plant the crop in the spring onto what is essentially bare soil. Well, I put the seed there. If there are no plants growing there, there are no roots. And if there are no roots, there are no mycorrhizae fungi. The biology doesn't exist. That incredible network of roots and mycorrhizal fungi, hyphae, is not there to recycle nutrients. So in cultivated soils, much of the year, only for 4 months, something like that, I've got a crop there. The rest of the year I have nothing. Well, the soils are vulnerable to leaching because I don't have that root hyphae network there to recycle the nutrients. Okay?
All right.
So when it rains, any excess cations can be kind of leached out. So again, we're really getting into the weeds here of chemistry, but
It's good though. I think it answers a lot.
This is cool stuff.
I'm into it. So let's stay in the weeds.
Okay.
Well, I have a
So
question.
this is of that soil evolution, and this is why one of the reasons why row crop soils tend to acidify. They acidify because we put nitrogen on there, ammonium nitrogen, which releases protons or hydrogen ions that make it acid, but also we tend to leach the base cations out of these row crop soils, and they get acidified. So we have to come in and periodically lime them, add ag lime, which is basically calcium carbonate or calcium and magnesium carbonate, to replenish it.
All right. So we have evolution of soils and clays over a long period of time, geologic time scale we've been talking. Now, if we kind of go on a much shorter time scale, human scale, I think a lot of people have experienced this in a row crop field in a garden. They start wanting to plant something, they start digging and they're pulling up chunks of clay. You know, maybe they're basketball size, really large, feels like clay, looks like clay chunks. When you start to put plants in that, people say, well, the clay goes away, but it's not going away. Are you just diluting out the clay with organic matter via roots, and maybe if you're mulching or manuring on top or composting on top, are you getting in between some of those clay bonds with organic matter? When you have a lot of clay, you introduce plants to it, what happens to that clay? Breaking apart? Is it diluting down? Is it just fracturing? Is it going away?
Well, on the time scale of a human lifetime, soils can evolve, but not very much unless there's erosion or deposition, right? You can lose massive amount of soil in a single storm one night if you've got a horrible erosion event. But if you're not having erosion, then the changes are relatively slow. You can observe some of those changes in a few decades. For example, if one of the things we saw in soils that were being acidified by large amounts of nitrogen fertilizer was that we were chemically altering the soil, and you were losing cation exchange capacity. And it was, the clay minerals were evolving so that, you know, you have freely swelling smectites with all these negative charges on the surface, but the interlayers were starting to get gummed up with hydroxides, with aluminum iron, which inhibited the swelling and inhibited the and blocked the cation exchange sites. So that can happen on the scale of a few decades. We could see a change, but for the most part, it doesn't change very rapidly. The mineralogy doesn't change. Organic matter is different. Soil organic matter is a very reactive and very important component of our soil fertility, productivity, and its physical properties. What is soil organic matter? It's you can think of it as dead plant tissue, microbes, but they have evolved. They are no longer, you know, certainly I put a leaf down there, you can recognize the leaf and you can watch the leaf decompose. Well, now you're releasing various organic molecules. Those molecules can be a group of amino acids, a peptide, right? Or it can be sugars, 2 or 3 sugar molecules linked together, saccharide, disaccharide, trisaccharide, or something like that. And you can have various chemical reactions that cause those to polymerize. Or you can add in a silicon or aluminum that would tend to coagulate those organic molecules. and you are producing over time what we call humus or humic substances that are present in the soil that give soils the black color. This humic material exists in a number of different forms, but think of it kind of as a fuzzy, furry film that sort of coats the mineral surfaces, fills voids between mineral particles, can fluff up the soil. Okay, you start taking your clay minerals and you cover it with humic materials, and they're going to be less likely to swell. You can even get some humic materials inside of the clays themselves, inhibiting the swelling. Humic materials also contain lots of other nutrients. So we've been talking mostly about cations like potassium, calcium, magnesium. But for a plant to grow, also needs nitrogen, phosphorus, sulfur. And these tend to exist as anions, negatively charged ions. The nitrogen can exist both as a positive and negative. It can exist as ammonium, which is a +1, or it can exist as nitrate, which is a -1. And it can be transformed between the two. Okay, it can also exist as an amino acid inside of that humic material. So typically, soil humus has a carbon to nitrogen ratio of about 10:1. And as microbes consume the humus, the nitrogen, which is part of the amino acids that is part of this humic material, gets released into the soil solution as an ammonium form. And plants can take that up. So the humus plays a very critical role in supplying particularly nitrogen, but also to some extent phosphorus and sulfur and other more anionic nutrients to support plant productivity. So really they work synergistically together. But what you're referring to is you talked about these chunks of clay. Well, of course, they're not pure clay. They're a mixture of clay, sand, and silt. But if you get enough clay in there, they can dry out and become quite hard. Yep. But you get enough humus in there, and you can basically sort of fluff it up. The humus has a low density, and it fills all these pores in between the particles and fluffs it up. It holds water, it provides habitat for microorganisms, and it provides food for microorganisms. So the humus, the soil organic matter, evolves relatively rapidly. Whereas I mentioned ago that the mineralogy doesn't change much on a human lifetime time scale. A little bit, but not a lot, unless there's an erosion event, that sort of thing. But the organic matter can go up and down, depending on how you manage that soil. If I'm putting lots of manure on, I'm keeping, I have a perennial crop, a grass crop, as opposed to a row crop, which is there just part of the year. I'm putting greater amounts of organic matter, fresh biological material, plant roots, leaves, stems, into the soil. I build up the organic matter. But if I, let's say I grew silage corn, right? And I was cutting that silage off, taking it away, and not putting anything back on that soil. I would cause rapid degradation of soil quality, and much of that would be due to the loss of the organic matter. Also, it would be due to removal of the potassium, calcium that are in the silage corn. Okay, so you can, in a lifetime, you can take a very fertile soil and make it very infertile, or you could take an infertile soil and build it back up, depending on how you manage it, what you put back in.
We have a sandy soil, dominated sand particles. Can you add clay to that soil and turn that into more of a productive loam? And kind of part two of that is, or if you took a sandy soil and added organic matter to it, probably the more likely option for most people in that situation, what would be different? So you take sand, you add clay and organic matter, or you take sand and add organic matter. Are you going to end up with dramatically different results?
So if I had a very sandy soil that has low clay, low silt content, just sand mostly, right? And I put manure on it, let's say, it can be productive, and the manure will help, but for a short period of time. That manure will rapidly decompose, it'll be oxidized, it'll be turned into carbon dioxide and other nutrient elements that are in the manure will either be taken up by a plant or leached out, and very quickly that sandy soil, you know, I get a flush of productivity from the manure, but then very quickly it's lost and I'm right back where I was starting from. Okay, clay works synergistically with organic matter. The clay minerals help to stabilize humus, soil humus, slow down its rate of decomposition, and help to hold not only nutrients, but water in the soil. So conceptually, and this is done in some parts of the world, I could put clay into a sandy soil and mix it up and throw in some manure and other organic residues, and I could turn a really lousy sandy soil into a nice productivity, a nice high productivity soil. I could make a brand new soil, a high quality soil out of a sandy mess. One of the key problems with sandy soils is they have low water holding capacity. If it rains, most of the water just percolates through the sand and goes on down into the subsoil. So if it doesn't, you know, I could plant a seed in there, and if it rains every other day, you know, I'm going to grow my crop. But if you get a 3-week period with no rain, that plant runs out of water and dies for lack of water. In a clay or a nice loamy soil where I've got a mixture of sand, silt, clay, organic matter, has a much higher water holding capacity. It's able to, the plant is then able to live on reservoirs of water that are retained in that soil and get through that 3-week drought until the next rain comes, and then keep growing. So the resilience is what that combination of clay and organic matter add to that soil, which is why it's so much better. You know, you can grow, you know, great crops in sandy soils if you've got a fertigation system. So you're irrigating it and putting in nutrients, and you're spoon feeding those in. You know, You can do it, absolutely. But you've got to have a very high level of management to do that. You got to spoon feed both the water and the nutrients to the crop in a sandy soil. Whereas in a loamy soil, you've got a much more robust and resilient system. And it requires, quite frankly, less management to get a good crop out of it.
So a lot of times you hear people talk about clay soils in a very negative way because of the work that may be associated with it. You know, it's hard to dig through, etc. It sounds like you're in this. I mean, you'd rather have that scenario because you can add organic matter pretty easily. You can put that in, and that's going to do a lot more for you than have a soil where, you know, you snap your fingers and that percentage of clay is a lot lower. And yeah, you know, the soil is like nice and easy to work, but you're giving up on all the benefit of having that clay in there.
Well, I wouldn't go that far.
Okay.
There's such a thing as too much clay. And I think a lot of farmers will tell you that. If you get too much clay, well, it can be tough. You know, it can get sticky. It holds so much water you try and drive through it and you get stuck. The soil can become impermeable. So you have rain landing on the soil surface. You don't want that rainwater to run off. You want that rainwater to soak in. You get too much clay in the soil and it doesn't soak in, it runs off the surface. You can have and if you're in, let's say, a depressional area and you've got a lot of clay in there, well, then water is moving in and it tends to be saturated. And plant roots need air. They need water, but they also need to be able to breathe. And if it's saturated for too long a period of time, it'll kill your crop. Unless it's rice, right? Some crops are engineered to survive, right? But most crop, you know, corn or wheat will drown if they don't have proper drainage through that soil. So what you're looking for is that balance. You know, everything in moderation, right? You want a good amount of sand, you want silt, you want clay, you want organic matter in the right mix, and you want porosity. You want holes, bubbles, air in there. And you want biology, so everything is turning over rapidly, releasing nutrients from the organic matter, and new organic matter being added. That's what makes the most productive soils.
So if you had a heavy clay soil in a do anything world, would it make sense to add sand to that clay soil to increase large particle size and break that clay up, dilute it out?
You certainly could do that. If it's in your backyard, right, your garden, and you're willing to pay $10 for a tomato, absolutely, right? If you're a farmer who's trying to earn a living by growing crops, it's generally not going to be economically viable to do something like that. The cost of moving sand into a clay soil, or vice versa, clay into a sandy soil, is, yes, it can be done, and yes, it can be effective, but often it is not going to be cost effective. It'll be too expensive, and you'll never recoup your investment from strictly a business perspective.
Knowing that this evolution of clay does occur over very long periods of time, and I agree with you. I mean, adding sand to everything, not practical, but seed is relatively cheap. I mean, could you make a difference in a farmer's lifetime, and not even a farmer's lifetime, but in a farmer's career economic lifetime by putting plants into the ground? Can roots break up a heavy clay fast enough to change the soil enough to actually make a difference? Or is that just sounds good in theory, but not in reality?
No, no, no. That is actually fairly widely practiced agronomic agronomy through crop rotations. Okay, if you grow continuous corn and your soil is starting to degrade, you could put it into a forage legume, alfalfa, for example, for a couple of years. And alfalfa has these magnificent roots that tend to break up soil, that tend to put in organic matter and humic and build up the organic matter and add nutrients to the soil. So a crop rotation that includes a forage legume is precisely what you're talking about, helping to build up the organic matter and the nutrient value of that soil. And this is what we did before we had synthetic nitrogen fertilizers. We used rotations. Some farmers still do, many farmers still do. It all sort of boils it down again to economics, though. What is do you have a market for that hay crop, right? But yes, absolutely. That's what management is all about. That's what crop rotations are all about.
Looking through some of the earlier work that you did, going back 15, 20 years, that was looking at a lot of clays and organic matter relationship. When you have organic matter in the soil next to clay, are they only interacting at those cation exchange points, or is there something else happening? Is that clay providing some sort of additional benefit to that organic
matter? Clays and organic matter definitely interact. Did a lot of electron microscopy trying to understand how all this, how the microstructure of where the organic matter is, where the clay particles are, where the sand particles are, how they interact. The clay can, for example, protect the organic matter from being decomposed. So I mentioned earlier about putting manure on a sand, right? And how rapidly that manure is completely, the word we use is mineralized, turned into carbon dioxide and to nutrients, and the nutrients are leached away, and the effect of the manure is gone, and there's virtually nothing left to tell you ever put it there. But in that loamy soil or soil that has higher clay in it, that manure carbon gets more, be more effectively integrated into the humic materials and will persist for a longer period of time. Clay is slowing down the rate at which it is decomposed. We don't know all the reasons why this occurs. Some of it is related to water and aeration. Some of it may be physical, like clay acting like a shield to keep the microbe from getting to the humic substance. Some of it may also be different elements like aluminum and silicon that are being bound up inside the humic material and making it more difficult for microbes to eat it. Think about it for a moment. If you had a nice a bowl of oatmeal, right? You know, and you're eating it, right? You know, that'd be pretty good, right? But if I put sand in that oatmeal and you try to eat it, it'd be a tough chew.
Right.
All right. Well, now think about it. I've got humic materials, and if I put a bunch of silicon and aluminum and iron in there, it's going to be more difficult for microbes to eat it. Okay. So there's a lot of things going on, processes, physical, chemical process that influence the biology that's going on in the soil.
Is that
And
dynamic?
those interactions are what build soil quality.
Is that changing dynamically? Meaning, if we looked at that soil under a microscope today, and then we came back 2 years later, might we see maybe the clay around the organic matter now, but 2 years from now, we might not be able to find that? You know, could that change over time based upon whatever's happening environmentally?
It is certainly dynamic. If you go out to a natural soil, I don't care, the sod in your yard, I don't know, wherever you want to go, right? You are constantly mineralizing the soil organic matter. Okay, so that means it's being consumed by microbes, and they're turning it into carbon dioxide, which is going off to the atmosphere. They're releasing the nitrogen that's part of the amino groups, for example, that are peptides that are bound up in the humic material. And that nitrogen is going through various cycles and being taken up by plants or being used as to build new soil microbe bodies, right? You know, new organisms, right? It's constantly being recycled. But there's also a living biomass there, the grass, the sod, and you've got roots that are growing, and you've got leaves that are being added to that constantly. So you're losing some, but you're adding some at the same time. Now, conceptually, you approach what we might call, it's not true equilibrium, it'd be more like a steady state is the terminology we'd use, where the amount coming in and the amount going out are roughly in balance. If, however, I left the soil fallow, I made sure there were no plants growing on it for 10 years. You know, I might start out with a soil organic matter of, I don't know, let's say 3%, okay? 3% by mass in my surface horizon is organic matter. I feel pretty good about a soil like that. 10 years later, and I'm just making up this number, but it might be down to 1.5%. You've lost a lot unless you've got something being added in. If you kept it fallow for that 10 years, you could lose a lot. Okay, because all that would be happening is the microbes would be chewing up the humic materials. You'd be emitting the CO2, but if you're not adding something back in, you're not maintaining the system. You are degrading it, you're mining it. This has been one of the big problems with row crop agriculture, is that, you know, we do add crop residues and roots, but we don't add enough often to maintain the soil quality. Here in central Iowa, back 200 years ago, this was prairie, right? We had this massive prairie ecosystem with these massive root systems, and you know, sure, the buffalo came through every now and then, prairie fires came through every now and then, but year after year we were putting carbon into the soil, and of course carbon was being mineralized and leaving the soil as CO2, but you had oftentimes 6-8% organic carbon in that soil. Beautiful, rich, black, loamy soils. Well, then we came in and we plowed up the prairie and we grew a crop that, that added only a small amount of residue every year. And we've lost at least half, maybe 2/3 of the organic matter that was in these prairie soils in the last 200 years of cultivation. Even though we've been, plowing down the crop residues, we've been still losing ground, been losing organic matter. And with that loss, we lose intrinsic fertility. Not always, not every farm is the same way. Farmers that have a good rotation, for example, have, put the alfalfa in there periodically. You could take this thing back uphill. But on average, across much of the Midwest, areas that had 6% organic carbon now have 2%.
Hi, everybody. Thanks for watching. Subscribe here to get the latest from the show. Also, be sure to check out some of the great clips and watch the full interviews right here on In Search of Soil.